Welcome to my video course on Communications-Based Train Control, CBTC. Have you ever stood on a totally packed subway platform during rush hour, checking your watch, watching a jammed train pull away, and thought to yourself, why don't they just run another train right behind it? It is a huge daily frustration for millions of urban commuters worldwide, right? We deal with congested transit, shoulder-to-shoulder crowds, and delays that just seem totally avoidable. Now, you might think the fix is easy. Just buy more train cars. But the truth is, the reason you are stuck waiting isn't just a lack of trains. It's an invisible limitation built right into the tracks themselves. So let's dive into this.
So why can't we just run more trains? It's a completely relatable question. You'd probably assume that increasing capacity is a simple fix, like just put more rolling stock on the rails. Well, adding more trains actually hits these unseen capacity bottlenecks and really strict headway restrictions. Now, headway is just the time or distance between two trains traveling in the same direction on the same track. In conventional railway signaling, there are absolute unbreakable rules about how close trains can get to one another to ensure they never, ever collide. So the track capacity is fundamentally limited by the mandatory separation between these trains. If you just cram more trains onto the track without updating the communication system, you just end up with a massive underground traffic jam. The traditional safety systems, which were designed decades ago, literally won't allow it. To truly grasp this bottleneck, we have to look at the legacy approach to train safety. I'm talking about systems like absolute and automatic block signaling. In these older setups, the railway track is chopped up into fixed, physical sections called blocks. The golden rule here is that only one train is allowed in a block at any given time. A key concept to know is block overlap, or BO. This is an adequate safety distance, traditionally around 180 meters in a lot of systems, that is strictly maintained between trains. It is essentially an artificial, rigid safety cushion. Because the old system can't pinpoint exactly where the train is within a block, it has to assume the absolute worst-case scenario. It forces this massive, predefined buffer zone to prevent trains from getting too close, totally regardless of how fast they are actually moving. Consider two trains operating in an automatic block signaling system. Because the system uses fixed, static blocks, it creates this massive gap of wasted space. It forces an artificial separation that is way longer than what is physically required for the trailing train to safely stop. The track circuits really only know that the leading train is somewhere inside its current block. Therefore, the trailing train is forced to stay entirely out of the preceding block, plus maintain that extra overlap distance we just talked about. This leaves huge stretches of empty, completely wasted track space that could absolutely be used to run more trains and get you to your destination faster. So, the crucial takeaway here is that conventional signaling relies on what's called a static speed profile. The block design is based entirely on the maximum permitted line speed for that specific area. It's a single, static rule applied to every single train. Because of this rigid design, the signaling system simply cannot adjust the safety distance based on the actual, real-time speed of the train. Now, contrast that with a dynamic speed profile, which is the whole foundation of modern control. A dynamic profile constantly calculates the exact target speed by looking at real-time braking curves. If a train is moving slowly, it doesn't need a massive distance to safely stop. The dynamic system recognizes this, whereas the static system treats a train crawling at 10 miles an hour exactly the same as one flying at 100 miles an hour. Crazy, right? Section 1. The solution. Moving to moving blocks. Let's break down how CBTC actually achieves this total paradigm shift. First off, in a true CBTC system, there are absolutely no physical trackside signals or track circuits dividing the rails into rigid blocks. None. Instead, CBTC replaces those with continuous, high-capacity, two-way radio communication between the train itself and the wayside control center. This is huge because it enables the real-time determination of the train's exact location with incredibly high precision. Because the system knows exactly where the train is and exactly how fast it's going at any given millisecond, it can perform dynamic calculations of safety distances. The result? Minimal artificial separation. The train and the wayside network establish a flexible, dynamic safety bubble that continuously moves with the train. To really grasp the magnitude of this difference, think back to a classic fixed block system. In that setup, the network cannot digitally pinpoint the train. It just assumes the entire block is occupied. Because of this massive blind spot, the trailing train has to stop completely behind the absolute fixed border of that block. That means it is stopping far away from the actual physical location of the leading train. Sure, it guarantees safety, but it is incredibly inefficient when you're trying to move large volumes of people. But then, look what happens under moving block working with CBTC. This is the real aha moment.
The moving block shrinks the occupancy zone from an entire rigid section of track down to exactly the rear of the leading train. The safety distance is continuously calculated. The wayside equipment establishes a protected area, called a movement authority, right up to the nearest actual obstacle, which in this case is literally the back of the train ahead of it. This continuous communication allows the following train to safely close that gap. They can run much closer together while perfectly maintaining the necessary safe braking distance. So let's summarize this showdown between the two concepts to see exactly why transit authorities around the globe are rushing to upgrade. With fixed blocks, your headway, again, the time between trains, is inherently long. But with moving blocks, it's incredibly short, often dropping down to just 90 seconds. For safety distance, fixed is static and rigid, forcing all that artificial separation. Moving blocks use dynamic, real-time calculated braking curves. And the ultimate outcome of all this? Track utilization. Fixed blocks leave us with low utilization and massive amounts of wasted track space. Moving blocks give us maximum capacity. By constantly calculating exact locations and adjusting to real-time data, CBTC drastically increases the overall number of trains you can safely push through a network. Think about what this means for a rapidly growing metropolis. How will this invisible technology reshape the future of your city's growth? Well, it means we can move millions more people without necessarily having to dig completely new billion-dollar tunnels. It means your morning commute gets faster, less crowded, and infinitely more reliable. And it's all thanks to a continuous, high-speed radio conversation happening invisibly all around you. It's just fascinating how shifting from static physical constraints to dynamic digital communication totally unlocks the true potential of our infrastructure. Okay, thanks. We'll see you on next video.